Good morning, everybody, and thanks for joining us for today's webinar. We're going to be focusing today on the topic optimizing your database for the cloud using DynamoDB with a specific focus on global secondary indexes, GSI. We'd ask you to use questions. There's a question box on your screen, and you can type your questions into that. We'll be getting to them during the session if we can, but we've left plenty of time at the end for Q&A, so we'll be covering those. And just a word on that, we won't be going into roadmap items, so if you do have, is this coming, feel free to ask it. We won't be answering those, but we do take that input anyway, and it's always good for us to keep in touch with what's important to you. So let's begin. My name is David Pearson. I'm joined by Siva Raghupati, who is going to go into the deep dive section. I want to start with a little bit of introductory information about DynamoDB, just so you're aware of some of the main concepts. So the first thing to understand is that it is a database service. It is one of a number of managed database services that we have at AWS, which give you the option of relational with our RDS, Relational Database Service, which supports 4 different engines: Oracle, SQL Server, MySQL, and Postgres. DynamoDB is the NoSQL managed database service. We also have managed Elasticache, which is a managed caching service which supports Memcached and Redis engines, as well as Redshift, a managed data warehouse service. So as a managed service specific to DynamoDB, the automation of operations is a key part of how the value is used by our customers to reduce the effort required to basically manage and scale a database. DynamoDB was also built on tenets of predictable performance, durable low latency, and being cost effective. So in regards to cost effective, we stress heavily that the design of the application is critical to that, of course, and this is what a lot of what today's session will be about. In terms of predictable performance, the very flat latency curve and the very high amount of throughput that DynamoDB can sustain gives our customers, the users of DynamoDB, the ability for their applications to sustain extremely consistent performance profile for their applications. So if we look at durable low latency as an example, writes are durable by using 2 different ways. One is persistence to disk, and one is redundancy by replicating it to other availability zones. And so both of those are extremely important in guaranteeing durability. And so the data is absolutely durable by design. Writes aren't even acknowledged until they're replicated and persisted. You can see from the chart there just an example of throughput versus latency, how flat the latency is preserved despite a very large variance in the degree of throughput. Reads, you get the option of eventually or strongly consistent, and there's no impact on latency for that. Now, a few recent announcements we've had during the year, the latter part of the year for DynamoDB. Just a quick recap. And the top point here, secondary indexes, is going to be the focus of obviously this session. So I'll leave that to Siva. And other things you may or may not be aware of, DynamoDB Local is an offline, like laptop-style development environment where you can build and test your applications without being connected to a network and, of course, without paying any throughput costs. Fine-grained access control is a feature that enables you to have your applications work directly with DynamoDB without having a middle layer required. And of course, we released other libraries for both geospatial and transactions. So these are the sort of developments we've been releasing in recent months. So let's start with a few core concepts. The primitive container structure for DynamoDB is a table, and within table is a collection of items. An item is a collection of attributes, each individually assigned at the item level. Now, when we talk about schema list, the schema is defined per attribute. So this is a differentiation from a relational database where the schema is defined at the table level. So this gives a great deal of flexibility in designing and growing applications into different areas of functionality. When we talk about attributes being optional, there is one exception in DynamoDB, and that is the hash. The hash key is used it supports the key value access pattern, and it's mandatory for all items in the table. And the reason it's mandatory is because it's used to determine and drive the data distribution. So while your table may exist on a single partition, as you scale it, we will use the hash key to determine where those items will be distributed to give you increased throughput. So from an application design perspective, choosing your hash key and making sure that they are highly distributable is very important. We also have the option of the range key. Now, range keys are an option. You can have a hash-only primary key, or you can have a hash range composite primary key. The value of the range key is really twofold. One is to enable one-to-many relationships represented within the table. So a single hash can have multiple range entries. The primary key enforces uniqueness across both of those attributes. More importantly and more useful for most applications are the rich query capabilities that range key enables. And this is key to today's webinar because we've basically taken this value of having range keys and the query ability against those range keys and represented that into our index structure. So when we talk about indexes, local secondaries, we have two types of index. The local secondary basically says on the same hash key, you can take a different attribute and make that a range key, an alternate range key. And our indexes are also sparse. So if you see in the example here, we're indexing, obviously we preserve the hash and we're indexing a new range key. There are only two attributes in that table that qualify, therefore the index is only populated with two items. The important part about local secondary indexes and why they're called local is by the locality to the hash key means that they are local to the partition as well. So the index and the table data are co-located. This gives us extremely high throughput and very low latency when updating indexes. So the net effect of that is that having an index or 5 or 0 on a table, the latency impact is negligible. So I'm going to talk a little bit about also global secondaries. We're going to introduce that as well. And this is obviously where we're going to spend more time today. Global secondaries differ by basically enabling you to define any attribute as a new hash key or a range key. So in this case, we've got a hash range table as the underlying table. We've chosen another attribute to promote that to a new hash key, and it's a hash-only index. So in that case, again, the sparseness of the index, you can see only 3 rows populate, and we have a new hash key value. So this gives you extreme versatility when you're building applications to optimize your access pattern. So what we're going to do now is pause. I'm going to hand over to Siva, and we're going to go much deeper into the structure of indexes, what's under the covers, and how to basically use them to optimize your application design. Thanks, Siva.
Hi, thank you, David. Let's sort of summarize, the differences between local secondary and the global secondary that Dave alluded to. So I want to go through 7 different points here. Number 1, in the case of a local secondary index, the key has to have, the index has to have a hash key, which needs to be the same as that of the table, and it needs to have a range key. And then in the case of a global secondary index, which will be going into the details, you can have a global secondary index with just either a hash key and a hash and a range key. So that gives you a lot more flexibility there. So in the case of a local secondary index, hash, same attributes. The hash needs to be same attribute on the table as we talked about. Range key can be any scalar attribute. Whereas in the case of a global secondary index, the hash key and the range key can be any scalar attribute, if you will. We'll walk through this in some of the examples here. One of the limitations potentially of a local secondary index, the size of both the data and the indexes that you have for a specific hash key must be 10 gigabytes or less. There is no such restrictions in the global secondary index. And the number 4, the query over a single partition as specified with a hash key value in the query. I think you can whereas in the query in the case of a local secondary index can only is specific always to a specific partition, because you're required when you query you're required to provide the hash key. Whereas in the case of a global secondary index, you can query over the entire table. In contrast to the local secondary, as I mentioned before, you can only query for a specific item collection pertaining to a hash key. The local secondary indexes, when you query a local secondary index, you can ask for an eventually consistent read or a strongly consistent read, whereas in the case of a global secondary index, it's always going to be an eventually consistent read. Now, read and write capacity units for the local secondary index come from the definition of the table, whereas in the case of a global secondary index, you will have to explicitly specify read and write capacity units for every index that you create on the table. In the case of a local secondary index, if you do not project those attributes that you want into the index, the query will automatically get those attributes from the base table. Whereas in the case of a global secondary index, you'll have to go 2 round trips. I think we'll go into the details, some more details on this. So I think this is a pretty important table to have. In some cases, you may have a scenario where you may use both the local secondary and the global secondary, in which case I think differentiator would be number points 4 and 5. Do you need, in the case of the 5, would you need eventual consistent, is eventual consistency okay or not? In some cases, it's the main decider. If you need the index to span across item collections, which is your hash keys, across all the partitions, if you will, then clearly you have to use the global secondary index. I want to go into the details of the GSI attribute projections. In this case, I have shown on the top is a table in A1, A2, A3, A4, A5 are various attributes of the table. In this table, I'm picking a table where it has only the key. The primary key comprises of just the hash key. So if that is the case, that table could also be a table with the primary key being a hash key and the hash range as well, which we will illustrate more through the examples. But what I'm saying here is, I have 4 indexes there. The first index has keys only. When you define a global secondary index, you can just say whether you're projecting just the keys only, or you could include specific attributes. In this case, the third global secondary index I've included attribute 3, or you can include all attributes. That is the last case there, where I have A4 and A5 as the hash and the range key. So these are all the various possibilities, if you will, when you define a global secondary index and what you can project. Automatically, the table key is projected. The base table key is projected in all the global secondary indexes that you create.
Siva, can you just explain what projection means there when you use that term?
Projection means those attributes are copied into the index. If you do not project the index, you'll have to go back and get those attributes from the primary table. I'll just cover that in the access patterns as we go forward. Thank you. This slide sort of leads into what David was trying to allude to. There's essentially a couple of query patterns with the global secondary indices. If the query is covered by the GSI, in other words, if you're querying for attribute A, B, and C, if all those attributes are part of the GSI, then you can simply query the global secondary index. And then the index will cover the query, in other words. But if you have attributes that are not covered by the global secondary index, you'll have to do 2 or more round trips. The first round trip would be you'd query the GSI and get the table keys. And the second round trip, would be potentially doing a get item if there's a single item is returned, a single key is returned by the query, or you could do a batch get item to get multiple items from the base table. So I think the key tip here is if you need very low latency, then project all the required attributes into the GSI. The caveat there is you'll need to provision more write capacity units and pay for more storage as well. So I think that's the trade-off that you need to go evaluate there. Going a little more deeper into how do GSI updates work. In this case, let's say we have a base table and we have 5 global secondary indices. In fact, the maximum number of global secondary indices that you can define on a table is 5. So from the client, you are updating a table. Let's assume that the update to that attribute, the attribute is in all 5 indexes that you specify, in which case what we do is we write to the table, we commit the update to the table, and send a response back that the update has succeeded. Asynchronously, in parallel, we also initiate an update to global secondary indices. Since this is an asynchronous process, the update to the global secondary index will be eventually consistent. But what we guarantee is that when the client gets a success message, 200 HTTP status code, that the update succeeded, the global secondary indices will be eventually updated. Typically, this happens within the order of 1 or 2 seconds. There are some caveats to that. For example, if you don't have the necessary provision throughput capacity, write capacity in the global secondary indices, we will try to update. We will hold the update and try to update later until a certain point of time, for a short duration, if you will. We'll go into the details of that more. So typically, the global secondary index should be consistent in less than a second or so. So one key thing to remember is that one table update can be 0, 1, or 2 GSI updates. So let's go through the scenarios where there will be 0 updates. Let's assume you have an attribute in the table, and then that attribute is not in the index. So index is not affected at all by the table update, in which case there's no reason to update the global secondary index, in which case there's 0 updates. And then let's take the other extreme, which is the 2 updates. Let's say if you're changing an attribute from A to B, and that attribute is reflected in the global secondary index, in which case what we do is we delete what's in the global secondary index, and then also an update. So that is 2 operations. The other 2 scenarios are when the update introduces a new indexed attribute, it is a simple insert into the GSI, in which case there's only 1 update to the GSI, or if the update deletes the index attribute, again it's a single delete in the global secondary index. So I think when you provision your write throughput units for global secondary index, so if depending upon your use case, you need to be aware of this fact. So in which case, let's assume if there are 2 updates for every single table update, you may want to provision twice the amount of write capacity units on the global secondary index compared to that of the table. So that's a very important fact to remember. So now let's go through some GSI examples. So I'm taking a scenario here. Let's assume we're building a multi-tenant application for file storing and sharing. So I think the first question to ask before you use DynamoDB is, what are the access patterns? In other words, what do I want to get out of the data that I put in DynamoDB? In this case, let's assume there are 6 requirements. Users should be able to query all the files they own, and users should be able to search by the file name. Number 3, search for the file type, search by a date range, and let's assume the users can share files as well, and users want to keep track of what files that they've shared. And then users also want to, let's say, search by the descending order of the file size. Let me find out what are the big files that I have. So if these are the requirements, then one potential design would be to use a couple of tables. Let's say a user table with the hash key for user ID and the attributes such as username, email, address, etc. And then the second table would be, let's call it user files table. It maintains the relationship between users and files, which is one user has multiple files. In this case, I'm using a hash key, user ID as the hash key, and the field ID as the range key. And the attributes may be name, type, size, date, a shared flag. And then let's assume you're potentially putting the blob data in S3, which is a simple Amazon Simple Storage Service. You would keep a pointer to the S3 key. I'm also building some global secondary indices for indexed access. In this case, for searching by the name, I want to build a name index. For searching by type, I want to build a type index. Similarly, for date index, And the shared flag, I want to index by the shared flag. So this is a sparse index. So only items that are shared, or files that are shared, would be reflected in the index. And also the last index is a size index, which is the attribute index would be the size. We'll walk through each one of these cases shortly. So let's assume you're querying for, find all the files owned by a user. You would query, for a specific user, you want to look up the user ID in the users table, which I haven't shown here. Let's assume the user ID is 2, and then you basically say, query the table where hash key equals 2, and then don't specify the range key. In which case, what we've highlighted here, the yellow highlighted records would be returned by DynamoDB. And then the second access pattern is search by file name. In this case, I'm using the name index. In the query, I specify index name equals name index, and then I'm specifying the hash key, which is the user ID equals 1. And then the name of the file is file1, in which case it returns a single record in this sample data set. Similarly, for access pattern 3, I'm searching for a file name by file type. In this case, I'm using a type index, and then the query may be, for a specific user ID number 2, for type equals dot, give me all the items. So as you can see here, I'm projecting the file name here. In this case, the query would be asking for just the file name back. If the file name is not projected, then I'd have to do a second get from the primary table to retrieve this. So projecting what you want in the query makes this a single round trip to DynamoDB. So in this case of access pattern 4, similarly, I'm just doing for a range query on a date. I'm just saying a date between 2 dates. Give me all the items. Again, I'm looking up the date index in this case to retrieve those items. Since the name is projected, I don't have to go back to the primary table to get the name from the primary table. This is the sparse index. In this case, since I'm only searching for files were shared by user 1, since the index will only contain only records that are shared or flagged for sharing. So that's example 1. And then for the last one, an access pattern query for file names by descending order of the file size. In this case, I'm using a size index, and then I'm saying scan index forward equals false, which means I'm going to be scanning the index in the descending order. In which case, file size 1000 would be the first record, if you will, and then the second would be the size 100, since we are only searching for user ID 1. I'm taking a second example here just to illustrate the difference between, the first example that I gave. You could have done that with both the global secondary index and the local secondary index. Doing it with the global secondary index, you don't have the 10 gigabyte restriction. Let's assume you have users or companies that are modeled as users storing, millions of files. You don't have to be constrained by the 10 gigabyte limit, and using a GSI allows you to not have that limit. So in this case, I'm using a second table. Let's assume we're dealing with a gaming scenario, and I have a game scores table which comprises of ID as a hash key, and then user, game, score, and date. Let's say in this case, Bob was playing game G1, and Bob has a score of 1,300 points, and the date, and then the date which Bob played that game. So you could simply log this data in a hash table with the format shown here, and then let's assume if the query was find top score for game G1, how do we do this? In this case, we could potentially construct a game score index with the hash key as the games and the range key as the score, and then the ID gets automatically projected. If you say index, in this case, I'm projecting attributes user and date, in which case ID will automatically, the index key, the table key ID will automatically project it into the index. So a query, then let's say that this would be the structure of the game scores index. As I mentioned before, you should think of a global secondary index as really a separate table that is automatically updated by DynamoDB. So the records in the global secondary index would be like the format I've shown here. Now, this is just if you go into the DynamoDB console, I've just, in this case, I'm running, I'm listing all the games. I'm using the global, in this case, I'm using the global secondary index, and then I'm specifying an equality condition on the hash key where game equals G1, and for a specific game, I'm looking at all the top scores. In this case, it looks like Mary had a score of 2,000 points, and she's the top. She has the, and then as you can see the list there, it's in the descending order of the scores. So that's another example of how you may use the global secondary index. Now, let's go into the data modeling with GSI. Oftentimes, when I sit down and model, try to model a scenario using DynamoDB, it is important I look for relationships. I look for one-to-one relationship, one-to-n relationship, and m-to-n relationship. What I'm going to go through now is what potential constructs you could use for modeling this in DynamoDB. In this case, I'm a user. I'm modeling a user ID, the relationship between a user. It's a one-to-one relationship. User ID and the attributes pertaining to the user. One way of modeling this would be simply using a table with a hash key and carrying on the other attributes. Another way of modeling this, let's say you have that user table and you want to search, you want another search path into the table, which is given an email name, obtain all the attributes of the table. In this case, I've constructed a global secondary index with the hash key as email. So in which case, let's say I want to find all the data pertaining to Bob, and I know the Bob's email is bob@gmail.com. Then I could look up that using the global secondary index. So this would be one way of modeling one-to-one relationship using the global secondary index. Let's assume we want to model the relationship between the users and the games. One user can play many games in this scenario. In which case, you could construct a global secondary index. In this case, I've called it the user games global GSI on the right side. The hash key that I've chosen is the user ID, and the range key that I've chosen is the game ID here. So if you use that index, you could simply say for user Bob, give me all the games that Bob played. So you would get the first record and third record, if you will, which would be, in this case, game 1 and game 3. So this is a way to use GSI to model one-to-many relationship, in which case you're using a GSI with the hash key and the range key. For one-to-one, you're using a GSI with simply a hash key. The third way is modeling end-to-end relationships. This is where the power of the GSI comes in handy. Before we had the GSI, literally you had to create two tables, and you had to manage, for example, a table similar to the in a game user GSI, and DynamoDB automatically manages the game user GSI for you. So in this case, if you had the primary table user games table and the GSI game user GSI, you could ask a couple of questions. Given a user Bob, give me all the games that Bob played. In which case, it would be game 1 and game 3. And then you can derive that data from the user games table. But if you want to ask the question the reverse way, given a game, what are all the who are all the players who played, let's say, game 1, in which case you would get Bob here, and using the game users GSI. Since this is automatically managed, the updates to game users GSI is automatically managed by DynamoDB. This is a very powerful way GSIs give you a very powerful way of modeling, end-to-end relationships. Now let's switch and go into switch context and go into some best practices. So what are the sort of the best practices with GSI? The first best practice is choose a GSI hash key with very high cardinality. In this case, I've taken an example table. Let's say in the table, and this is an employee table with the ID as the hash key and the name, sex, date of birth, and address. So let's assume you chose, sex as the hash key. There's only two, there's potentially, there's two possible values, male and female there. So if you have thousands of records or hundreds of thousands of records or items for this, then all of them would have only a cardinality of 2, in which case the number of partitions your query cannot scale beyond the global secondary index cannot scale beyond a couple of partitions, if you will. So I think the way to solve this problem would be probably generate a prefix, let's say M1, M_1 to M_100, a prefix or a suffix of, let's say M_1 to M_100, and then use that, use that as the value that you would use for sex, in which case what happens is we could potentially create, this data can be spread across 100 partitions, if you will. That gives you 100 orders of magnitude more throughput, if you will. So that is, that's something, GSIs give you a lot of power, but at the same time, one needs to be careful in not to put a hash key on an attribute that has a very low cardinality. If you run into that situation, you could use this mechanism to still use the power of the GSI. The second advantage is we sort of walked through this in the sparse index example I gave in the multi in the first example I walked through. But let's consider a second scenario here, sparse indices. Let's assume the games table that we talked about before. Let's assume if somebody has 1,800 points or more, they're called a champ. Hopefully, in your data set, potentially there's a hard game and there's only a very few champs. And if the query is to find out, give me all the champions for this game or the champs for this game, if you could simply create let's say an award GSI in this case, called with the hash key, with award as the hash key, that GSI will only contain for this data a single record. So rather than actually going through the entire table to query this, you could simply query the global secondary index and then materialize the result. So sparse indices come in very handy for sparse data types, and it's a very powerful, GSIs are very powerful constructs for dealing with sparse tables or sparse attributes. The other best practice here is let's assume you have a table. In this case, I've called it the mailbox table. And then let's assume this mailbox table has a large number of attributes. In addition to it has a large attachment. So if you want to, if you are throwing up a quick screen that shows just a few attributes, for example, who did you receive the email from, date the email received, etc. Let's assume 3 attributes of that nature. And then there is no point in scanning or querying the entire table and paying the read capacity units. One way of actually reducing the cost there would be to create a mailbox lookup GSI and simply carry those 3 attributes that you want to prompt. And once somebody picks those attributes, you can always go back to the primary table, let's say, and get the large attachment. So this is one way of reducing the consumed read capacity units. I think this is perhaps the most important thing, best practice to follow. The key here is you should provision enough throughput for GSI. As we discussed before, one update to the table may result in 2 writes to an index. So you should provision in that case twice the amount of write capacity units on the GSI. If GSIs do not have enough write capacity units, the table writes will be eventually throttled down to the slowest index can consume, right? So let's assume, just a practical example would be, let's assume if you have a table with 20 write capacity units and you had two GSIs, let's say they had, 1 or 2 write capacity units. So if you start inserting data into that table, what will happen is we allow for bursting. If you, let's say, consistently insert more than 20 writes per second to the table, into the primary table, since we allow bursting, you may be able to insert about 30 or 40 records for some time. Then it'll eventually get throttled down to 1 write per second. Even though you provision 20 write capacity units for the table, you'll be only getting 1 write capacity units because your slowest index has a write capacity unit of 1. So this is a very key point for you to consider, and I want to call that out. And I'll give you mechanisms to troubleshoot this scenario in a moment. So this brings up to the next question, which is, well, what happens when, in the scenario that I mentioned before, if the table gets throttled because you're doing, let's say, 20 write capacity units and the global secondary index is just only 1, you'll get an error message, for example, status code 400, provision throughput exceeded exception. So one good practice is to always log your error messages in your app tier, for example. In this case, the error message would be the level of the configured provision throughput for 1 or more global secondary indices of the table was exceeded. Consider increasing your provision level for the underlying provision global secondary indexes with update table API. The key thing is this error message does not have or does not show the global secondary index that was causing this, right? So how do we find that? That brings up to the next slide, which is the CloudWatch metrics. For every global secondary index, we surface several CloudWatch metrics. For example, we surface provision read capacity units, consumed read capacity units. We also surface provision write capacity units as well as consumed write capacity units. So if, let's say, a specific GSI was the core reason for throttling that was happening, and hence you got that error message 400 that we talked about before, you will see read throttling events or write throttling events. In the example that we talked about, you'll see write throttling events metric, a number against the write throttle, how many requests are getting throttled by the GSI, and the write throttling events will show you that. And then you can also see, you can also compare your provision write capacity unit versus consumed write capacity units, right? So if in this case, if it's 1 and 1, obviously you're completely consuming all the write capacity units. It's time to update your write capacity units on the global secondary index. I think this is perhaps one of the key thing. A few customers are running into this. There's a few forum posts as well on this topic. I just wanted to make sure I covered that here. With that, I want to just summarize and open for questions. I think the summary here is global secondary index is a very powerful feature. It gives you 5 different access paths into your base table, and which is really, really powerful. And like we talked about, global secondary indexes, sparse indices. You can create sparse indices, or you can create you can carry along attributes in the global secondary index and make your application extremely fast. And one thing you need to remember is you need to remember to provision enough provision write capacity units to the global secondary index, so your writes are not throttled by the global secondary index. And with that, we would like to take some questions. Thank you.
Thank you, Siva. That was great. So we're going to pause, and we've got a lot of questions in the Q&A. So if you have any more, please type away. If you could stay on as well at the end, at the conclusion of the Q&A, we've got a brief survey that we'd love your input on to help us guide us towards serving you with better webinar content going forward, and a few other things. So let's cover a couple of these. A couple of easy ones. Is there a limit, a maximum throughput rate for DynamoDB?
I think there's no maximum throughput limit for DynamoDB. I think you can, if you go into the limits, if you search for DynamoDB limits, we will actually, in the books, we will show you what the, we put an artificial limit on every service because we don't want to have any runaway queries, that is a surprise for us or you. So if what is in our limits is not adequate for your use case, you can just simply fill out a form, and then we can provision. We can increase the limit, and you can basically do any amount of read or write capacity units.
Yeah, thanks. I think the principle of distributed systems is when they're well architected, there is no theoretical limit except that imposed by the amount of data you have. So it's achieved by striping the data more broadly, and so a certain amount of data will only stripe so far, and then you're down to the individual storage rate for each item. So in our case, that's a hash key. But yeah, there is no theoretical limit to DynamoDB.
Yeah, another way of saying that would be you can provision the amount of writes you want. If you have a large number of cardinality and your workload is uniformly spread across your hash keys, then that should be evenly distributed across partitions, in which case there is no upper bound on how much read or write capacity units, reads or writes you can do from Dynamo.
Great. What sort of performance delta can we expect from GSI queries compared to normal queries?
Like we talked about, I think if your index is going to cover the query, it would be simply your normal query. If the index does not cover the query, you'll have to go back to the second round trip. So that depends upon the number of items that the primary query, the index query returns. So it could, yeah, so it depends. So if performance is key, you should project the attributes in the index so you don't have to do 2 round trips or more.
Yeah, and part of your content there, you spoke about taking the gender or the sex of the sex as the field and basically increasing the cardinality of that.
Yeah.
Can you explain a little bit about the benefits of that, why you do that? I think we talked about how you do that, but can you understand, like, help the audience understand why you would do that, and in which cases that would make a good thing?
Yeah, I think as you pointed out earlier in your slide, David, I think the partitioning by DynamoDB is automatically done, and the hash key is used as the mechanism for partitioning. Let's say if you had, so I think the more the number of hash keys, the more partitions we could create. If you have, let's say in this case, the cardinality is 2, potentially, the maximum number of partitions that you could have is potentially 2 or very small. We partition for a couple of dimensions. We partition for throughput and size. And then even though we partition for throughput, typically, most queries with that kind of cardinality would land in a single partition. If you query for, sex equals male or sex equals female, your query can only be materialized, in a single partition. All your queries will go to the same partition, if you will. That makes it challenging. That is the main reason for, the workaround or the best practice suggested there, which is to use underscore 1 to 100 and spread the query. In which case, I think it's a little bit of when you get let's say if your question is give me all the males, then you will have to actually, let's assume if you use the suffix of 100, you'll have to literally run 100 queries to get that, right? You could sequentially or parallelly run that. So I think I just want to make sure that you're aware of that piece as well.
And I think it's important to point out that best practice is obviously, it's optimal for taking an application or a schema to any degree of scalability. But these sort of practices are sometimes not even, not necessary if you're running very low volume. So make these judgments. You don't have to necessarily design for absolute maximum throughput. If you're very confident that your application is never going to get above a few dozen or a few hundred operations a second, let's say, then you have many more options available to you. We don't tend to spend time on those because obviously there is a ceiling there that you will hit if you do scale through that. But if your application, if you're very confident it never will, you could use a low cardinality hash key, for instance. We have people doing that, but just be warned of the potential impact of that if you try to scale it. And that's just basic design, right? It's not specific to Dynamo. So we talked about the maximum number of GSIs per table being 5. So I just want to reiterate that because we got that question. I have a question. Is it necessary? Why is it necessary to mention the index name in the query?
Yeah. I think it is necessary to, I mean, that is the query API design. So if you are, and maybe the query is, why can't you automatically find the index based on the query? I think the query API, I think one thing, we're very conscious, I think when we design Dynamo, what we want to do is we don't want to, I think we want the performance, the same performance at any scale. So I think making the developer conscious of what index to pick allows them to think about scale right at the design stage. I think that is one of the considerations, but I think you do have to specify the name of the index as part of the query.
Yeah. Question, is the hash always projected into the GSI?
Good question. I think it could be if your primary table is just a hash table. Let's assume you have a primary. If the primary table is just a hash table, then if your, let's say, GSI is the hash for the GSI is different from, and the range, if you will, is different from the hash in the table, then yes, automatically if you say, in the case of projected attribute, you have three options, right? You have keys only, and you have include, and then you have all. If you said keys only, yes, I think we would just include just the hash. If your primary table comprises of hash, hash range, a composite primary key, then that composite primary key is projected if it is not already a part of your global secondary index hash or the range key there.
Great. And can you explain, it's a very strong concept in relational where you can select from multiple objects, tables, indexes, and so on, and then join them. Obviously with non-relational you don't have that, but how would you construct the same sort of thing where if you had 2 or 3, say, indexes and you needed the data, you needed to query those to get the data back, how would you basically intersect those?
You know, it's a good question. In some cases, I think you'll have to do the join sort of, if you're joining 2 or 3 different tables, you'll have to sort of materialize the join, if you will, on the application side. I think that's one way of thinking about this. I have worked on other scenarios where potentially if you're searching for equality on one condition and a range on other scenario, what you could do is you could concatenate those 2 attributes and call that a third attribute, which is a concatenation of attribute A on A2. So you would simply have to construct a query which would say, let's say for a specific hash key, the range key may be a composite range key, in which case you're concatenating 2 attributes, if you will. Let's say for a particular device type, if the range comprises of, let's say, a combination of a device type and a timestamp. So you could just simply say for a device, for this concatenated key, something begins with, you have the construct called begins with, you know, type T1. That would basically give you everything of type T1. So you could do a concatenation of your range key and materialize some of the AND conditions, if you will, when the AND condition is equality on the prefix and the range on the second.
I got it. So a question on how it's implemented under the covers, which I think we can go into a little bit. A GSI can have duplicate keys, but the table cannot. So basically the question is, how do you implement that, and what's the value, what's the benefit of that?
Yeah, I think we don't have the case for GSIs without, you know, we're not going to go into the details of how we implement for IP reasons, but from a user perspective, it is a very powerful construct to be able to have non-uniqueness in the GSI because you know you have much richer query pattern. You know, we have 5 different access patterns into the table, and if not enforcing the primary key constraint, if you will, on the index gives you a lot very rich query capability to model.
Great. We've got a few minutes to go. So just a quick question on when we talk about partition and we talk about hash.
Yeah.
Is that a one-to-one relationship? because I think we need to clarify that. One is the physical layer, one is the logical layer.
Yeah.
Let's clarify what that means.
Yeah, obviously, you don't see the partitioning information from a user perspective. This is one of the, this is a managed service. We didn't want to burden you with how we partition. Rather, I think we wanted that to automatically happen. So as I was mentioning before, we partition either for size or throughput, but potentially if you, for a specific hash key, and then we use the leading hash key to partition. You may probably loosely think of that as, we run it through, let's say, a hashing function, and then spread through n number of partitions based on the hash key. That would probably be the simplest way to think about that.
Okay, great. So I wanted to ask a question about the sparse schema and how people can take advantage of those. So if we have, let's say, 1,000 items in the base table, we create an index on an attribute, and that attribute may or may not be present in each of those items in the core table. How can people design such that they can create attributes that keep their indexes really light and therefore reduce the read capacity required to access the data?
Yeah, and in the example we talked about, I think the sparse index, in the case of a file sharing, let's assume you have thousands of files and potentially have shared only 2 files with someone. So there's no point in scanning your entire table or querying your entire table with thousands of files to find out what is shared. In fact, if you construct a sparse index based on the sharing flag, the sparse index, as I mentioned before, has only items that have been shared. And therefore, let's say if you shared only 2 files of the thousands of files that you may have, it is much easier to go through the sparse index and then materialize those files, rather than if you just want to show what the file name is, you can simply include that as a projected attribute. So therefore, you can simply query the index and materialize the file rather than querying or scanning through thousands of files.
Great. So while we don't answer roadmap questions, there is one where we've already given indication that we will build that, and that is the question on online indexing. So just one point is that indexes are currently created at the time of table creation. So to move from the current the non-GSI or LSI table to one that has those indexes, you will need to unload and load that data back in, having to find the new structure. We have committed that going forward, we haven't issued a time frame, but obviously that's important to us to make that an online operation. So you can expect that. We've got a lot of questions on roadmaps. I'm just trying to filter them out. Even though I answered one, we won't be doing that. Can you explain a little bit about how, I know you covered it on the storage and therefore the cost and the throughput, the implications of having a GSI. So can you explain kind of when a write is written to the table, how that propagates through and what implications that has on storage and cost?
Yeah, I think there's storage and there's 2 dimensions here. One is the amount of data that you store. The other one is the provisioned write capacity units, if you will. When you're let's take the scenario of you're inserting, you have a primary table and you have global secondary index or one or more global secondary indices. As we talked about, a specific insert into the primary table can translate into 0, 1, or 2 inserts or updates into the global secondary index. So in terms of provision throughput, you may have to provision twice the number of write capacity units in one or more global secondary indexes, depending upon which attributes are carried forward. That's one dimension of cost. The other one is storage. So, we charge, I believe, 25 cents per gigabyte per month per storage. That includes, the size of the bytes that you put in, I believe, 100 bytes overhead in addition to that, both in the table as well as in the index. So I think the more, let's say, projected attributes that you have, the more global secondary indices that you have, and depending upon what's propagated to the index, So your costs, you'd be paying more cost. So in other words, you're trading off storage. You're trading off storage costs. In other words, you're paying more cost for better latencies, right? So that is the trade-off. So I hope that answers the question.
Yeah, great. And we had a couple of questions saying, when would I use Dynamo over something else like Kinesis or RDS? These are multiple questions. Could you explain maybe the best way to understand how DynamoDB is optimal for what situations versus something like a relational database and even maybe Kinesis?
Yeah, I think I want to generally look at, I think best reference would be, I think I gave a talk, a Riemann presentation, AWS storage and database architecture best practices, that I go through the entire spectrum of storage that AWS offers. In short, I think there's a few dimensions there. One, whether you're dealing with structured data, unstructured data, and with a simple query or a complex query. Typically, NoSQL databases, including DynamoDB, falls under structured data and simple query pattern. So let's assume if you have complex queries, such as group bys, order bys, even though Dynamo gives you some ordering, you cannot say, order by, group by, for example, right? So if you have a lot of summarization queries, etc., clearly a SQL engine or a relational data warehouse such as Redshift is a great engine to put that data in. Whereas if you have very simple structured data and very simple query pattern that we went through the walkthrough in these examples here, clearly DynamoDB is a great choice. I think those are a couple of dimensions, but I think I go into it further. There's a few more dimensions are what I call hot data, warm data, and cold data. Things like Elastic Cache and DynamoDB deal with hot data sets. In other words, you're writing thousands or hundreds of thousands of writes per second. And then typically what relational databases are not able to take that because they don't scale beyond a single box for most engines. So in which case I think DynamoDB is a fantastic choice in that scenario. So it's a combination of, in my mind, what hot data or cold data, and then the structure and your query pattern.
Thanks. We've got time for a couple more. So a quick question, what's the recommended way of backing up DynamoDB tables?
It's a great question. I think we have, if you go to the DynamoDB console today, we have automatically wired up the data pipeline to be able to actually back up within the region or across region. In fact, you can even move the DynamoDB table from one region to another region. So that, a lot of customers are using that as the preferred backup mechanism for DynamoDB. Either you could be backing from Dynamo in one region to another region, or you could be backing from Dynamo to S3.
Great. And we'll do one more, just with a quick reminder that once we've concluded this, there will be a short survey. We'd really appreciate your input on that. When importing data from DynamoDB into Redshift, does it consume read throughput, and how do you calculate that?
Yeah, that's a great question. So there's a copy command in Redshift that you can point to a DynamoDB table and have that table copied into a Redshift table. That incurs read capacity units. And you can, let's say if you have production workload learning in Dynamo, you can use a certain percentage. As part of the copy command, there is a parameter that says use X% of the read capacity units. So what we do is we just only use, let's say, 20% or 30% that you can mention of the read capacity units of Dynamo. That makes it, that ensures that your production workload is not impacted by the copy.
Thanks, Siva. And so that concludes today's webinar. We're going to be hosting another one at the end of February, so please join us for that. I think the invitations may be out there, and it was already associated with this one, so you can see we're launching into some best practice design there. We did that in a workshop in person, and it was very popular, so we decided to expand that to a